All right, we got one more topic, and that is a very important topic on equilibrium, the concept of equilibrium and stability. Okay, so to understand like equilibrium and stability, let's take a look at these three models that we just came up with in the um, first three examples in this lecture. All right, so we came up with this model of exponential growth. Now, if you look at the slope field for this differential equation for which results in exponential growth, you can see kind of the family of curves. Now, if we don't have any population, right, if we have a population of 0, that is not going to change, right? Unless you sort of, introduce some sort of population. But once you do introduce a little bit of population, and it's unconstrained, then it'll grow exponentially. So you can see down here, if we're down here at 0, whoops, I can't draw a straight line, but it's not going to change, right? If the initial population is 0, it's just going to continue to be 0. But you introduce a little bit of population, and it's going to grow exponentially. So you can kind of see what the curves are going to look like. All right, let's take a look at a logistic growth. Now again, if you don't have any population, it's just going to stay 0, right? It's not going to go anywhere. But if you introduce a little bit of population, it's going to grow, but it's not going to grow forever. It's going to grow until it reaches this carrying capacity. So you get this this sigmoid shaped curve. So let me try and draw that a little bit. So our carrying capacity has to be about here, right? This straight line. So with 0 population, you don't go anywhere. Add a little bit of population, and it's going to go to the carrying capacity. Now, if your population is at the carrying capacity, it's going to stay at the carrying capacity. All right, it's not going to change. If your population starts out above the carrying capacity, right, even a little bit above, it's going to the population is going to decline back down to the carrying capacity. Okay, so you can see we have these equilibrium solutions. They're called equilibrium solutions, where the population or the rate of change of the population becomes 0, right? And so let's look at one more example here. We have Newton's law of cooling. So if you start out with a hot cup of coffee, it's going to cool down to the ambient temperature. It's going to look something like that. If you have a glass of water that's already at the ambient temperature, the room temperature, then the temperature is not going to change. It's just going to stay at that ambient temperature. Now, Newton's law of cooling also works for heating. So if you start out with a cold glass of water, straight out of the refrigerator, then it's going to, the temperature is going to increase, and it's going to increase until it hits that ambient temperature. Okay, so you can see here we've got another solution that is kind of a solution where everything likes to end up at that ambient temperature, right? Just like in logistic growth, everything kind of likes to end up at the carrying capacity, and at that point, once it reaches the carrying capacity, the population doesn't change. And the same way with Newton's law of cooling, once it reaches the ambient temperature, it doesn't want to change anymore. Okay, so those are called equilibrium solutions. All right, so let's look at these definitions. So the equilibrium solution is constant for all values of the independent variable. So if it's an equilibrium solution, if that dy dx or dp dt or dt dt or whatever the rate of change is, when that is equal to 0. And an equilibrium is stable if a small change in the initial conditions gives a solution that tends toward the equilibrium at that as the independent variable changes. All right, so what that's saying basically, if you if a population is at its carrying capacity and you tweak the population a little bit, maybe you go out and you kill some deer, right? Then that population will rebound, assuming that the deer population is growing. It'll go back to its carrying capacity. All right. So, and the same way too, if you have a glass of water and you tweak its temperature, maybe you drop an ice cube in there, brings the temperature down, but then it's going to eventually want to reach that equilibrium state of the ambient temperature. So an equilibrium is stable if it wants to tend toward that equilibrium, whereas it's unstable is if you tweak it a little bit, if you tweak the population, and then it veers away from the equilibrium. So an example of that would be like this exponential growth, this first exponential growth. If you have zero population is an equilibrium solution, right? Because dp dt is 0, but you tweak it a little bit, and the population is going to take off if it's unconstrained. Okay, so and actually I'm starting to answer some of the questions down in example 4, but that's fine. In the logistic growth model, the p equals 0, population of 0 is an equilibrium solution. But if you change the population a little bit, then the population is going to grow until it reaches its carrying capacity. So that p equals 0 equilibrium solution is unstable. So kind of a classic representation of an unstable versus stable equilibrium is this car on a hill. So if you're at the top of the hill, your car can maybe sit there for a little bit, but if you push it a little bit backwards or forwards, it's going to roll down the hill, right? So that the car at the top of the hill is at an unstable equilibrium point. Whereas the car at the bottom of the hill, if you push it forward a little bit, it's going to want to roll back to the bottom of the hill. And if you push it backwards a little bit, it's going to want to go back to the bottom of the hill. So that place at the bottom of the hill in that second car is that stable equilibrium, right? Because if you tweak its position a little bit, it's going to want to roll back to where it was. So here's how we find equilibrium solutions. You just set the derivative equal to 0, right? So if you have some differential equation where y prime is equal to g of y, you just let y prime equal to 0, and you can find the equilibrium solution. So let's summarize what we said about the exponential growth. So where does p, so if we want to know what are the equilibrium solutions for the exponential growth model, dp dt is equal to rp, right? That's our differential equation. And we don't want to set that equal to 0. And that means that's going to happen when p is equal to 0. But if we tweak it a little bit, right? If we introduce any sort of population, it's going to want to grow exponentially. So this is an unstable equilibrium. Okay. So now if we look at the logistic growth model, so we have dp dt is equal to rp times 1 minus p over k, right? So when does that equal 0? So that equals 0 when p is equal to 0 or p is equal to k, right? So you're either at 0 or you're at the carrying capacity. And if p is equal to 0, right, and we tweak it a little bit, and becomes a little bit greater than 0, then it's going to take off. So this is an unstable equilibrium point. And when p equals k, right, then if p is equal to k and we tweak the population a little bit, it's going to want to go back to that carrying capacity. So this is a stable equilibrium point. And then finally, Newton's law of cooling, we have dt dt is equal to minus k T minus T sub A, the ambient temperature. When does that equal 0? Well, that's equal to 0 when T is equal to the ambient temperature. All right. And again, we have to think about, okay, what if we tweak it a little bit? What's going to happen? So if we tweak it a little bit, if we increase the temperature a little bit, it's going to want to decline back down to the ambient temperature, or if we cool it a little bit, it's going to creep back up. So this is a stable equilibrium point. All right, well, that's all I've got. So you should be ready to work on the discussion questions, and I'll see you in class.